In this video, we'll continue our discussion of section 6.1. What we're going to do now is the important part of the important reason that we learn these series is because we can take these functions. If you take a look, these are all, most of these are called transcendental functions, meaning it would be very hard to calculate by hand. Like I can't calculate like a polynomial. It's not like that. They have different types of relationships. So what makes this very important for us is that these Maclaurin series or Taylor series are used to represent these transcendental functions as a polynomial. So notice like this can become nothing but powers and division and multiplication and addition, right? It just becomes a polynomial with the sine and cosine too. It's very important, very powerful that we can represent these things as a polynomial rather than just sine. Just because of the way they work. A lot of your calculators will be using this to calculate a decimal rather than using sine in its like natural sense. It uses this to come up with these decimals. All right, so what we're going to do is we're just going to take a few functions and try to express them as a series. This won't take too long, but it's important that we understand why these exist. Why do we even study these? All right, so I have e to the negative x over 2. If I use, and maybe we could do this instead. This is negative 1/2 x, right? And we can use the series that was on the last page. Okay, this is going to be the summation from n equals 0 to infinity. I'm going to get 1 over n squared. That's part of it. And then it was x to the n. So I'm going to put negative 1/2 x to the n. I just plugged it in where the x would have been. All right, so if I work this out, if n is 0, remember 0 factorial is 1. We'll just leave that there. We won't talk about it. Let's just leave it alone. Okay, 0 factorial is 1. And then if I plug in 0 to the other one, I'm going to get a 1. Then I add it to the next term. Okay, if I plug in 1, I get 1 over 1 factorial, which is 1. Negative 1/2 to the x to the first power is negative 1/2 x. So I'll represent it like this, 1/2 x. Okay, if I plug in 2, all right, I'm going to get 1 over 2 factorial, which is a 1/2. But then I plug in 2 to 1/2 and I get 1/4 plus 1/2. I get a 1/8 x squared, right? And then the next part, if I plug in that was a 0, 1. If I plug in a 2, 3, we're at 3 now. 1 over 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. So I got a 1/6. I'm going to keep that in my head. And then 1/2 to the factorial is 2/3, which is 1/8. This is going to be, and since it's the third power, it's minus. It's going to be 1 over 48. X to the third. Right, and if we were to keep going, I'm going to go ahead and grab this number for you. You could check it. We get 384 plus x to the fourth plus dot, dot, dot. Okay, so that is our answer. That is our series for e to the negative 1/2 x. The more that you go out, like if you pick x equals 5, you would plug in 5 into each x, and that would give you an approximate. If you did the first two terms and you just plugged in 5 for x, it's going to be very inaccurate until we start adding in terms. The more terms that you add in, the more accurate your decimal will be. All right, this next one gets a bit tough. We're going to just rely on a computer. I won't ever ask you for something like this. It's really strange. But I could even take e to the x times sine x and multiply their power series. So if I look on the next page, last page, I get 1 plus x plus 1/2 x squared plus 1/3 x cubed plus 1/4 x fourth. That was the e to the x. And I'm going to times that by the sine. Sine was x minus x to the third over 6 plus x to the fifth over 120 minus x to the seventh over 50/40 plus dot 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 dot. All right, so we could multiply those. There's a way that your book has went about it, and they like ended up multiplying one by a bunch of things. It gets kind of confusing the way they set up. So I'm gonna write it, let you stare at it if you want to try to figure out. I will never ask you to do this. I used a computer to go forward, but this is what your book wanted to show. We're gonna have 1 times x, 1 times x squared, 1 or times negative 1/6 plus 1/2 x cubed plus negative 1/6 plus 1/6 x to the fourth, and it goes on and on and on. Well, this actually just turns out, and this is the computer part, x plus x squared plus 1/3 x cubed minus x to the fifth over 30. It gets pretty crazy, but we're just going to leave it. I just want to show you that you can multiply these things out. Now, how you get to here, is pretty difficult because you're taking an infinite series times an infinite series. It looks like they look to see what would multiply to get like terms like x to the third, x to the fourth, and then just put them together for representation. I will not ask you to do this. I just want to show you that it exists. I can multiply things like that. All right, we have one more here, and this is a pretty straightforward one. So if I do ln of 1 minus x, so I'm following that same thing they had up here. So let's go back up and look real quick. Ln of 1 plus x is this. So to change it, what I'm going to do is just put negatives in because it's a negative x, 1 minus x. So we're going to have negative x minus x squared over 2 minus x cubed over 3 minus x to the fourth over fourth. The reason that's happening is that the positives under the cubes or odd powers turn negative because the negative would produce a negative coming out. You could, if you'd like, to go ahead and put parentheses around each one and multiply it out. Well, this actually reforms into a summation as n equals 0, as of negative x to the n over n. You can see that pattern right above. All right, this is just a reminder of how these things work, why they're important, is because they represent these crazy functions like sine, ln, things that would be hard to calculate by hand, and they turn them into a polynomial, which makes them much easier to deal with. All right.